Hello everyone. So in this video I will be talking about an interesting question. It is to find the number of simple cycles in a graph and to actually find all the simple cycles in a graph. Now in an undirected graph. So the logic behind the way I will solve this problem is that I have a graph. I will construct a subtree in that graph, or you can just think about a minimum spanning tree. I will construct an MST out of that graph, and all the edges which are not used, these edges will definitely contribute to a cycle which are not in this MST. So they are basically some part of the cycle. Now I'll take each of these edges which are not used, let that edge be x to y, then I will find out the lowest common ancestor of x and y, and the cycle will be the lowest common ancestor of x and y. Let the lowest common ancestor of x and y be w. So the cycle will be the path from w to x, the path from w to y, and the edge xy. Right. So let's try to implement it. Number of nodes and vertices of this graph. This is an undirected graph. I'm just yeah, now I'll just create a set which will store all the edges. Because it's undirected, so I'll put both of them. Right, so now I'll start a DFS which will just construct an MST. I don't need to apply Kruskals because there are no weights, so every edge is equal, so I can just start a DFS from any vertex. And it is also important to note that I am definitely imagining that the graph is connected, because if it is not, then I won't be able to get a tree. I will be then getting a number of trees which I don't want. Okay. Okay, now if I am visiting a particular edge, then I will just erase that edge from my set of edges. Right. I'll just do a DFS from here now. Okay, now I want to construct I just initialize a parent array because I want to start right. Oh, I don't need to do this actually. Just right. Good. Okay, so now I'll make a tree. Right. Now the parent can also be -1. So if it is -1, we'll just continue. So I have got my tree here, right? So this is very easy. I just constructed a tree out of a graph. I can do MST, I can do Kruskal's or Prims or whatever, but that's fine. I can do this, right? So now what I need to do is, on this tree I need to find out the LCA. So for that I'll use something of a there is on Topcoder there is an article on finding LCA and log n time. So I'll just be doing that using a sparse matrix. So I'll do that. I'll not be explaining how it is working. The size is n log n, right? Sorry. I'll be using a height or depth, whatever you can call it. Parent is not -1, then we increment the height, right? Sorry, I was thinking about tree. Okay. But before we go here, we just need to pre-compute the previous ones. Okay. Parent of x and then I minus 1, right? 1 second, let me just check. Parent of x and I, okay. If y is equals to parent, we continue, or else we do a DFS2 and y minus, right? So I think this should do it, right? Just put this as 0. Okay, let's find out LC of x and y. This is a very easy function actually. If height of h is less than height of y, we just swap x and y. Then we start from the parent of x I is greater than 0 and it is above, sorry, it is below actually, because its height is, so we then if x is equals to y, we just return any one of them because we have found our answer. If they, now we are just bringing them to the same level. If they are not, if now they are at the same level, parent of xi is not equals to parent of yi, and we return, so this should do it, right? So now let us just call DFS2 1 comma -1, right? Now it's on tree, right? We just have to check it should be on tree, not on graph, right? So now what do you do is you go through all the edges which have not been visited. The edge is from x to y. This is your LC. Now what do? We have to find out the path from WW to XX and WW to YY. Right. So how do we do that? We just use a simple BFS. Right. We make a distance matrix. Because it's a tree, you can just use a DFS. There is no problem there. We initialize all of its distance as 0. We make a Q. While not of Q dot empty. Actually, this should let this be as starting vertex. Now X is Q dot Q dot. Actually, I just missed out these things every time. This should be tree. Okay, now if distance of y is greater than distance of x plus 1, then distance of y has to be distance of x plus 1. Okay, so for this okay, we initialize the parents as -1, so the parent of I has to be equal to, so y has to be equals to x, and we push y into this, right? So this is we call BFS once. We only need to call BFS once from WW, right? So we get the path from WW to everything, right? So the number of nodes which are sorry, let's this be x6, while current is not equals to -1, we see out current. Right. Current is xx, so we print xx, then its parent, then xx. Okay, that's cool. Right, so this should do the trick. You can take any let's see if it's possible. This should do the trick. So what is actually happening here is, this is quite an easy thing to do. What is actually happening is that we are inserting the edges. We are doing a DFS1 on it. This takes O of n time. Then after this, when we are doing the DFS on this, we are basically constructing this and another DFS2 on the tree, right? Another DFS2 on the tree, and for the DFS2 we are basically pre-computing the LCA table. This is the LCA function which will return the query. This should be correct. Yeah, okay, then we are using a BFS function because it's a tree already, so we don't need Dijkstra or anything else. It's a tree, so we use BFS, to get the distance, and while we are updating the distance we also update the parent from where it is coming from. Okay, so we are actually getting the shortest path or the only path, because in a tree there will only be one path, right? So you can just run a test case on this. I'll just tell you a square graph. Okay, 1 2 3 4 5 6, right? So let's just 6 6 6 6. So the number of vertices are 4, the number of edges are 6. So 1 to 2, 2 to 3, 3 to 4, 1 to 4, and then 1 to 3, and then 2 to 4. Yeah, so the cycles are 1 3 2 1, 1 3 2 1, 1 4 3 2 1, 1 4 3 2 1, correct? 2 4 3 2, 2 4 3 2, 3 2 1 1, 3 2 1. 3 2 1 1 is not a valid one, but still 4 3 2 1, 3 2 1. It is repeating again because of the number of edges. See, I'll just correct it. If you want it correct, I just correct it. Wait. Just dot erase. Yeah, this is why it is repeating. One 3 2 1, 1 4 3 2 1. Yeah, so these are the cycles: 1 3 2 1, 1 4 3 2 1, and then 2 4 3 2. Although there are more cycles here, but it is giving you the cycles which it depends on the MST then. So this question basically depends on the MST, but it will give you the number of vertices which are in a particular cycle. Like 2 4 3 2 are in a particular cycle, 1 2 3 1 are in a particular cycle, and 1 2 3 4 1 are in a particular cycle. So it will give you that, right? It might not give you the number of all the cycles, but it will give you the vertices which are in a particular cycle. So time complexity is again the number of cycles into n. So O of V plus E into the number of cycles. So kind of like that. So basically it is equivalent to Johnson's algorithm for directed graph, but you can definitely improve this. This does not give you all the cycles. Johnson's gives you all the cycles. Okay, thank you.